Have you ever just looked up at the night sky and wondered what it actually takes to sever our gravitational ties to Earth forever? I mean, really, permanently leave. Well, in today's explainer, we're diving into one of the absolute most fascinating concepts in all of physics, breaking free from gravity's invisible grip. To really understand this, we first have to talk about that invisible tether holding us all down. Think about throwing a baseball straight up into the air. Obviously, gravity immediately grabs it, slows it down, and pulls it right back into your glove. But let's push this thought experiment to the absolute extreme. What happens if you propel an object upwards with so much kinetic energy that gravity, which stretches out literally to infinity, can never quite bring it to a halt? The ball just keeps going. It outpaces gravity's ability to decelerate it. That magical threshold, that's what we define as escape velocity. It's the minimum speed an object must reach to break free from a celestial body's gravitational pull, entirely without any further propulsion. And hey, that last part, without any further propulsion, is absolutely crucial. This isn't about an elevator or a spaceship continuously firing its thrusters. I mean, if you had an infinite fuel supply, you could theoretically drive to deep space at 1 mile per hour. But escape velocity is purely ballistic. It requires one single, massive initial burst of energy. Once you hit that speed, you can cut the engines entirely, and you'll still coast away forever. Okay, let's pop the hood and look at the engine room of this concept, the math of freedom. The whole idea of escape velocity comes from a really beautiful concept, the conservation of mechanical energy. It's basically a cosmic balancing act. For an object to just barely escape a planet, the kinetic energy you inject at launch has to perfectly offset the planet's gravitational pull. So step one, you can think of gravitational potential energy as a negative number, like a deep well you have to climb out of. Step two is providing the kinetic energy at launch to start the climb. And step three is the perfect balance. You arrive at an infinite distance away, completely exhausted of energy, with your total energy equaling exactly zero. When you take those energy concepts and actually solve for velocity, you get this remarkably elegant little formula. Velocity equals the square root of 2 times g times m divided by r. Now, g is just the universal gravitational constant, which means this rule applies to literally every single object in the cosmos. It takes the sheer mind-bending complexity of leaving a planet and boils it down to just 2 variables, the mass of the planet, which is m, and the planet's radius, r. So the gravitational tax you pay is based solely on how heavy and how dense the world is. But honestly, what's truly profound here is what's completely missing from that equation. Did you notice? The mass of the object you're launching isn't there. Because the mass of the projectile perfectly cancels out in the math, the escape velocity required for a tiny feather is exactly the same as it is for a massive multi-stage rocket. The speed requirement is literally identical. And, assuming you don't crush into a mountain, it doesn't even matter what direction you launch in. Escaping a gravity well has nothing to do with you. It's entirely about the geometry and mass of the world you're trying to leave. Now, quick side note, because it's super important to distinguish escape velocity from orbital velocity. People mix these up all the time, but they are totally different states. Entering orbit is essentially just falling sideways fast enough that you keep missing the ground. That orbital velocity, which mathematically is just the escape velocity divided by the square root of 2, keeps you in a stable loop. Escaping, on the other hand, means severing the tie entirely. You don't need to hit escape velocity just to put a satellite into orbit. You only need that massive surge of speed if you intend to never, ever come back. So, what do these cosmic speed limits actually look like in our neighborhood? Let's compare the gravitational tax of our home to our closest neighbors. To leave Earth, you have to hit a staggering 11.2 kilometers per second. Just to put that into perspective, that's roughly 40,000 kilometers per hour. Compare that to Mars, which demands less than half of that at 5 kilometers per second, or our moon, which needs a mere 2.4 kilometers per second. This huge discrepancy dictates literally all of our space mission planning. Earth's mass makes it a remarkably deep gravity well to climb out of compared to the rest of the inner solar system. But if you want to truly appreciate how mass scales up gravity, get a load of this number: 618 kilometers per second. That is the velocity you'd need to escape from the surface of our sun. Tying it back to our formula, the sun's immense mass creates a gravity well so ridiculously deep that the energy required to escape it jumps exponentially. It's a vivid reminder of just how deeply anchored our entire solar system is to this one central star. And pushing this to the absolute cosmic extreme brings us to the ultimate trap. What if an object becomes so incredibly dense, its mass packed into such a tiny radius, that the gravity becomes overwhelmingly intense? Well, eventually, the required escape velocity hits c, the speed of light. And here's the kicker. The math doesn't break. The universe just enforces its absolute speed limit. Since absolutely nothing can travel faster than light, nothing can coast away. That exact boundary, where escape velocity equals the speed of light, that's what creates the event horizon of a black hole.
Let's bring this all back down to Earth for a minute and look at the rocket reality.
While the pure chalkboard physics of tossing an object to infinity are straightforward, actual human engineering has to negotiate with a messy reality. We absolutely do not instantly accelerate rockets to 11.2 kilometers per second right there on the launch pad. If we tried to instantly hit 40,000 kilometers an hour at sea level, the friction from our thick atmosphere would incinerate the vehicle in a fraction of a second. To get around this, we use staging, gravity turns, and parking orbits. We accelerate gradually, pushing through the thick air first, before firing those final massive burns in the vacuum of space to officially break the tether. Once a space probe finally clears the atmosphere and actually achieves that escape velocity, it gets to experience this beautiful mathematical irony. See, gravity gets weaker with distance, specifically falling off by the square of the distance. So the further out the probe travels into the void, the weaker the planet pulls back on it. The object is constantly losing speed, constantly bleeding kinetic energy, but the rate of that slowdown gets smaller and smaller. It will technically be slowing down forever, but because the planet's pull is continuously fading away to nothing, the object will never ever be stopped. Gravity really is a tether that stretches across the entire universe, touching literally everything. Yet, as we've seen, it's not an inescapable prison. With enough raw energy, humanity can and does outrun the gravitational bounds of our homeworld forever. But as we look up at the stars and dream of traveling to those heavier, denser super-Earths we keep discovering across the galaxy, it leaves us with a massive question. Will our engineering ever be powerful enough to let us escape from them if we actually manage to land?